Detecting and preventing overfitting and underfitting. In this video, we'll see how to detect overfitting and underfitting problem. Let's start by importing the libraries. We are using an inbuilt dataset from sklearn. Let's create x and y variable by using make classification. Let's create a sample size of 9,000 and feature of 18. Let's keep the an information as 4 and n redundant as 12. And pick the random states as 4. Now we have created x and y variable. Let's split our data into test and train. Let's split the data into 30 and 70. 70 for training and 30 for test. Let's create an empty list for train score and test score. Let's create the values. We're checking for 21 values, so that's the reason we're using 21 from range. Let's create a for loop for model and decision. Here we're passing the I values. We will check how our model will be performing for different depths. We are fitting the model here. And let's create a train v-hat. It is nothing but model predict for xtrain. Set the accuracy score for the train. Let's do the same thing for test. Also, let's append these values to our empty list. Let's try to print that. We'll keep it up to 3 decimal places. For a different value of I, let's see what will be the train accuracy and test accuracy. This is what we're going to test. As you can see, we have got the accuracy for various train and test. So let's plot that. Here you can see for one depth train, the low accuracy is around 84%, and the test is 82%. So there's a scope for improvement, but still there is accuracy, and so this is referred to as underfitting. Whereas in the overfitting problem, you see the depth is 20. It is able to predict 100% on the training set, whereas in test, it is performing poorly, which is 93. So that's how we identify whether it's an overfitting or an underfitting problem. We will learn how to prevent that in our upcoming videos. To prevent overfitting problem, let's import cross-validation. There are other methods to overcome the overfitting problem. You can increase the training set or remove unwanted attributes, or there is regularization and boosting which will come in the later stages. Let's create a param grid. Criteria we are taking are Gini and entropy. We are taking depth up to 20. With all these parameters, let's create a grid search. We're using a cross-validation of 3. So a job is basically parallel processing, and scoring is based on accuracy. So let's add this to our training dataset. Let's take the best parameters or best estimator. You can see the best estimators are entropy with max depth of 10 and minimum samples split of 5. Let's print the accuracy for both test and train and check whether we are able to work on the overfitting problem. Let's do the same thing for test. You can see for sample set 10, previously it was 98% and the difference was around 4%. However, the difference has now reduced, but we have to fine-tune furthermore to make the difference as close as possible. That is when we can claim that the overfitting problem has been resolved. That's how we prevent overfitting problem. And when it comes to underfitting problem, we will usually try out different models to increase the accuracy. That's how you prevent underfitting and overfitting problem. Regularization. Regularization is a form of regression that shrinks the coefficient towards 0 to reduce the complexity of the data. It reduces the variance of the model without an increase in bias. This technique discourages more complex models and prevents overfitting. Fitting involves a loss function, also known as the residual sum of squares or RSS. RSS is nothing but the difference between the actual and predicted value. The RSS is calculated using the equation you see on your screen. In this equation, y is the independent variable, beta is the regression coefficient value, x is the dependent variable. Let's now discuss the different types of regularization. Dropout regularization works by removing random selection. The more units that drop out, the stronger the regularization. This type of regularization is good for training neural networks. Early stopping is a second type of regularization where we use a large number of epochs and plot a validation loss graph. The training stops and the model is saved when the validation loss moves from decreasing to increasing. Co-adaptation is another type of regularization where neurons predict patterns in the training data by relying almost exclusively on the output of specific neurons instead of relying on the overall network behavior. If the validation data does not contain the patterns that cause co-adaptation, it could cause overfitting. Dropout regularization reduces co-adaptation because dropout ensures neurons cannot rely solely on other neurons. Lasso regression, or L1 regularization, is a category of regularization that penalizes weights in proportion to the sum of the absolute values of the weights. It helps drive the weights of irrelevant or barely relevant features to exactly 0, which removes those features from the model. Finally, ridge regression, or L2. Regularization will shrink coefficients close to 0 for those predictors that are unimportant, but it will never make them exactly 0. In other words, the final model will include all predictors. As you can see, there are different techniques that can be adopted to prevent overfitting. We will discuss regression and its applications in the next videos. Let's have a quick recap of the lesson. We learned that supervised learning is a machine learning model which identifies patterns and methods, learns from them, and gives predictions on a new set of data. There are two types of supervised learning algorithms, namely classification and regression. We also discussed the application of supervised learning in different industries like manufacturing and production, waste management and forecasting, data preparation, and the different steps involved in the process. How to detect and prevent overfitting and underfitting. Regression and applications. Aura's development team were deep in discussions about which regression model would be most suitable to predict audience preferences. So Sheila decided that she needed to have a more in-depth knowledge of the different types of regression models. She will explore linear regression in more detail and identify the ideal ways to prepare data for linear regression. She will learn how to identify linearity between variables and plot a correlation map. She will dive deep into how to shape, train, and test a linear regression model. She will also focus on how to implement a logistic regression model and also learn how to calculate the outcomes and accuracy of the model. Her next target would be to understand how to implement a polynomial regression model and test the model. She will also learn how to implement a ridge regression model and a lasso regression model. What is regression? Regression is a supervised machine learning technique which is used to predict continuous values. Regression is a process of establishing a relationship between dependent variable x and independent variable y. It is the easiest and one of the most widely used machine learning algorithms. More specifically, regression analysis helps us to understand how the value of the dependent variable changes corresponding to an independent variable while other independent variables are held fixed. It predicts continuous or real values such as temperature, age, salary, price, etc. Regression algorithms plot a best fit line or a curve between the data. Application of regression. Oil and gas industry. In oil and gas industries, various types of data are collected from surface and subsurface to understand the production and sale. Linear and nonlinear regression models are used to forecast global oil production. Regression analysis was used to influence factors on the future economy of crude oil. Regression models are greatly used to predict events that have yet to occur. Predicting the number of people who will pass in front of a particular billboard, predicting this, the company can place their advertisement accordingly. With this understanding, let us explore the types of regression models in the next video. Regression types, intro. Let's now discuss the various types of regressions that are used in machine learning. These are linear regression, polynomial regression, support vector regression, decision tree regression, random forest regression, ridge regression, lasso regression, and logistic regression. Linear regression is a popular modeling technique. It is used to predict a continuous dependent variable based on an independent variable. It uses the least square criterion for estimation. This technique can be applied only if there is a linear relationship between the variables. Polynomial regression is a form of linear regression. Here, the relationship between the independent variable x and dependent variable y is modeled as an nth-degree polynomial. Support vector machine regression. SVR is a supervised learning algorithm. SVR aims to create the maximum data points within the boundary lines and the hyperplane. This can be used for both regression as well as classification problems. Decision tree regression is a commonly used supervised learning approach. This method builds a tree-like structure. The internal nodes represent the test for an attribute, branches represent the test results, and the leaf nodes represent the final result or the decision. A decision tree starts from a root node or parent node or dataset. It then splits into left and right child nodes or subsets of the dataset. These child nodes are further divided into children nodes. They themselves become the parent node of these children nodes. Random forest regression is an ensemble learning method that uses bagging or bootstrap aggregation techniques. This method combines multiple decision trees to predict the final output. The aggregated decision trees run in parallel and do not interact with each other. Ridge regression technique is used while dealing with multicollinearity data. Here, the least squares are unbiased and variances are large. Predicted values will be far away from the actual values in these cases. Lasso regression is also a form of linear regression. LASSO is an acronym for least absolute. Shrinkage and selection operator. LASSO uses shrinkage and performs variable selection or feature selection. We'll discuss the different types of regression in more detail in the upcoming videos. Linear regression. In linear regression, while the dependent variable is continuous, the independent variables can be either continuous or discrete. The nature of the regression line is linear in this technique. The relationship between the dependent variable y and one or more independent variables, x, are established using a best fit straight line, also known as the regression line. Simple linear regression. If the value of a numerical dependent variable is predicted using a single independent variable, then such a linear regression algorithm is called simple linear regression. The equation used in simple linear regression is y equals mx plus b, where y is the dependent variable. M is the coefficient of regression, x is the independent variable, and b is the intercept. Multiple linear regression. The multiple linear regression algorithm uses more than one independent variable to predict the value of a numerical dependent variable. The equation used in multiple linear regression is y equals m1x plus m2x plus up to plus c, linear regression line. A line showing the relationship between the dependent and independent variables is called a regression line. A regression line can depict two types of relationship. Positive linear relationship. If the dependent variable increases on the y-axis and the independent variable increases on the x-axis, then such a relationship is termed as a positive linear relationship. Negative linear relationship. If the dependent variable decreases on the y-axis and the independent variable increases on the x-axis, then such a relationship is called a negative linear relationship. Applications of linear regression. There are many applications of this technique. For example, linear regression is used to administer the sulfur cap rule by the International Maritime Organization. If a company uses fuel that emits more than a certain amount of sulfur, they will be heavily fined. However, the company would incur a huge cost if it used any other fuel. So the only solution is to use fuel with sulfur within the sulfur cap. Machine learning is used to measure how much sulfur is being released in the exhaust, and what can businesses do to reduce the sulfur content from it. We will move on to discuss data preparation techniques in the next video. Working with linear regression. Let's start by importing the data. We are using sklearn datasets. We will be using the housing dataset. Let's create a data frame. This is the housing dataset. We will be predicting the price of a house based on the attributes available. Let's try to describe it. As you can see, the mean house price is 2, and the maximum is 5. Now, let's check if there are any missing values. All columns in the data frame are good. There are no missing values. Next, we'll visualize pairwise relationships in the housing_df data frame features against house price using a pair plot. So here you can see a pair plot with scatter plots for each feature plotted against house price. It provides a visual overview of the relationships between the variables. Next, we'll plot the geographic distribution of data points based on longitude and latitude. The size of each point represents the population, and the color indicates the house prices, offering a visual representation of how house prices and population density vary across different locations. Based on the plot, we can see that houses closer to the ocean, shown in red, tend to be pricier, while those closer to the land are in blue. This suggests a correlation between proximity to the ocean and higher house prices. Next, we'll check for multicollinearity using the variance inflation factor, VIF, for each predictor. First, we compute the correlation between feature variables and visualize it using a heat map. As you can see here, the heat map displays correlation coefficients between housing-related variables, with values ranging from -1, blue, to 1, red. High positive correlations are evident between variables like average rooms and average bedrooms, while medical insurance and house price also show a notable positive correlation. So next we will compute and display the absolute correlation values of house price, sorting them in descending order. The absolute correlation values between house price and other variables are calculated and displayed, sorted in descending order. This facilitates the identification of the most influential predictors strongly associated with house price. For example, medical insurance exhibits a notably high positive correlation, indicating it's a strong predictor for predicting house price. Now let's plot the scatter plot to better understand the relationship between medical insurance and house price. You can see here the scatter plot showing the relationship between medical insurance and house price from the housing_DF data frame. The plot has medical insurance on the x-axis and house price on the y-axis, with data points represented in blue. Next, let's calculate the variance inflation factor, VIF, for each feature in the housing dataset to identify multicollinearity. The VIF helps determine the correlation between predictors and drop features with high VIF values. So, as you can see here, the output reveals that latitude and longitude have exceptionally high VIF scores, indicating severe multicollinearity issues with other predictors. Addressing these features is crucial for improving model stability and interpretability. Next, let's remove the latitude and longitude columns from the housing_DS dataset to eliminate highly multicollinear features. Now, let's convert selected columns in the housing data frame to numeric and add a constant to the features. Then fit an OLS regression model using stats models. Let us now perform residual analysis to validate linear regression assumptions and visualize the distribution of residuals and their relationship with predicted values. We will also discuss the significance of the model coefficients to understand how each feature influences the target variable. The histogram displays a somewhat normal distribution with noticeable right-sided tails, suggesting the presence of outliers in residuals. The scatter plot showcases residuals against predicted values. Ideally, random scatter around the zero line is expected, but there are some residuals with particularly large positive or negative values, indicating potential outliers affecting the model's accuracy. The model coefficients indicate the impact of each feature on the house price. A positive coefficient for medical insurance suggests a positive correlation with house price, while average bedrooms shows the most significant positive influence. Now let's compute and interpret the R-square and MSE metrics to evaluate the performance of the linear regression model on the housing data. So here the model explains approximately 54% of the variance in the dependent variable, with a mean squared error of 0.61, indicating moderate predictive performance. Let us now visualize the distribution of several predictors and the target variable using box plots to identify potential outliers that might impact the model evaluation. The function plot_boxplots displays box plots for each column in the housing data frame, offering insights into the distribution and presence of outliers for individual features. Here, you observe outliers in features like medical insurance, population, and house price, which adversely affect model performance. It's essential to address them for improved model accuracy. Now let's create a function, remove_outliers, that iterates through each column to calculate the lower and upper bounds based on the interquartile range and replaces outliers with these bounds. This approach preserves dataset integrity by retaining potentially valuable insights from outliers while reducing their impact on statistical analyses and machine learning models. The clean data frame housing_df_new is returned without the outlier values. Let us now visualize the distribution of predictors and the target variable in the clean data frame, housing_df_new, using box plots to observe the impact of outlier removal on the data distribution and potential changes in the feature ranges. This will help in assessing the effectiveness of the outlier removal process. The diagram above depicts the dataset features after replacing outliers with the lower and upper bounds. It ensures extreme values are within reasonable limits. Let us now fit the linear regression model on the clean data frame, housing_df_new. The selected columns are converted to numeric. A constant is added to include the intercept, and then the OLS regression model is refitted to evaluate the model's performance after outlier removal. Now, let's visualize the distribution of residuals and the relationship between residuals and predicted values for the refitted linear regression model on housing_df_new.